So let's continue new chapter, chapter 12. This is the last chapter for this course, refrigeration and air conditioning. In chapter 12, we'll discuss fans and building air distribution. Right? When we say fans and building air distribution, that is very obvious that fans that can be a fan, it can be a blower, and the distribution we use, I mean the air distribution from the outside air to the zone where we require the air conditioning, or the return from the conditioned space to the outside, whether for the exhaust or for the recirculation, that is being carried out with the help of ducting. So in this chapter, we'll mainly discuss the two chapter, fans and then the ducting. So there is a difference between fans and blower. We'll discuss in the coming slides. In today's class, we'll discuss just the fans, and in the next class, we'll discuss the ducting, inducting, that mean the duct design, sizing, and different types of the duct. So the first one is fans and blowers. If we look at the objective of the fan, fan is an essential component of all heating and air conditioning system. Essential mean without the fans you cannot move air from outside into the conditioned space, and similarly for the recirculation from the conditioned space to the outside. So that means this is compulsory component of the heating and cooling air conditioning system, right? Mainly, the you know that the purpose of the fan is to move air through the ducts and to induce air motion in the space against a resistance caused by the ducts, dampers, or other component in a fan system. So that's the main objective of the fan, right? So what do you think? Is there any difference between fan, blower, and compressor? So do you think there is any difference between these? Because all of these three components, whether it is a fan, blower, or compressor, the three of them, they are used for the gases, for the air, right? They are used to increase the pressure mainly. So what's the difference then between the fan, blowers, and the compressor? Anyone has any idea the difference? Uh, as per ASME standard, they differentiate between the three component, fan, blower, and compressor, on the basis of specific ratio, right? On the basis of specific ratio and the increase in system pressure. I mean, specific ratio, let's say this is a blower, let's say this is a fan, and fan has one is the inlet, let's say, and this is the outlet, let's say. So the ratio of the outlet pressure to the inlet pressure, that's called the specific ratio, right? And increase mean how much increase in pressure. So these two parameter give the difference between these three. When we say fan, fan has maximum specific ratio up to 1.11, and at that can increase the pressure up to 1136 millimeter of water column. Normally the pressure in the duct, they are measured either in inch of the water column or the millimeter of the water column. So they can have maximum increase in pressure up to this value. Similarly, when we differentiate between the fan and blower, the specific ratio in the blower is between 1.11 to 1.2. And similarly, they have increase in pressure up to 2066 millimeter of water column. Whereas the compressor, when we say the compressor, they are also a pressure increasing device, but when they have the specific ratio more than 1.2, and they can increase pressure up to, I mean, more than the 2066 millimeter of the water column. So this is how we can differentiate between the fan, blower, and the compressor. Usually, I mean, when we speak in a general term, the difference, I mean, you cannot, there is no much difference between fan and a blower, right? The only difference is the pressure. I mean, when we say blower, the blower generally mean for high pressure. As you can see, the specific ratio is much higher than the fan. And when we say fan, there that mean they are mean for the low pressure application, right? And when we say compressor, when you require a very high pressure, right? I mean more than when you have the specific ratio more than 1.2. And then the different types of the fans and blower, uh, depending upon the types of the flow, we can categorize the fans into centrifugal flow fan and the axial flow fan. When we say the centrifugal flow, I mean the airflow changes direction twice, once when entering and second when leaving. I mean the direction of flow entering is different than the leaving one. No, generally the direction is perpendicular to the entrance and the leaving, whereas in axial flow air enters and leaves the fan with no change in direction. I mean, there is no change of the air direction when it moves through a fan. Those called the axial flow fan. Similarly, the blowers are of two types. One is the centrifugal flow and another one is the positive displacement blower. Centrifugal blower and the centrifugal fan, they are likely the same thing. The only difference is the pressure they have created, whereas the positive displacement blowers are those blowers that provide constant volume of the air. Right, and now let's discuss one by one. The first one was a centrifugal fan. Right, as you can see from these two pictures, the first one, as you can see, the centrifugal fans, they can be belt drive. I mean, the electric motor, they are mounted with a pulley, as well as the blower is mounted with a pulley. So they can be driven with the help of a belt arrangement, a pulley and belt arrangement. Whereas they can have the dual arrangement as well. For example, in this picture, the same centrifugal blow fan or the centrifugal blow, they can be directly connected with the help of a coupling. For example, this is a motor, electric motor, on which we can mount a coupling and a shaft, so they can be directly coupled with the help of the blower. They have the dual arrangement as well. There is an access hole for mounting the bolts as well, right? So you can see a different component of the centrifugal fan. As you can see, this is the blower, right? And these are the different coupling, the mounting, and this is the casing. Let's say if the air entered from in this direction and it will leave from this direction. I mean, this is perpendicular to each other. Similarly, let's say the air enters from this direction and it will leave from this direction, right? I mean, the principle that is used to increase the pressure in that centrifugal fan is we use the centrifugal force. I mean, because of the rotation of the electric motor, because electric motor is directly coupled with the blower, so the blower will move with high velocity, same velocity as if it is directly coupled with the electric motor. So it will have same velocity RPM as the velocity of the blower. So that velocity is basically converted into pressure with the help of that volute casing, right? In general term, I mean, I'm talking about journal. I mean, when we say centrifugal fan, they mean they are for high pressure application. When we say high pressure, that means the pressure above than 500 millimeter of. When the pressure is, I mean, more than 500 millimeter of water column, then we say a high pressure, right? The medium pressure is between the 100 to let's say 500, and the low pressure mean the less than the 100 millimeter of the water column, right? So in general term, the application of the centrifugal fan is for high pressure, right? I mean, high pressure mean to overcome the resistance of the ducting, the overcome the resistance of the fitting and the clampers and dampers and the diffusers, right? So mainly, I mean, when let's say the length of the duct is too high, I mean, the distance is too large from the place where you have to deliver the air. That means then the pressure drop will be much higher. So that means you need a blower, you need a fan that has the high pressure that can produce the high pressure, so that to overcome all of the losses that are coming in between the conditioned space and the blower, right? Their efficiency varies from 60 to 83%. Generally, they have a good efficiency. The efficiency can reach up to 80%. I mean, the mechanic overall efficiency, that means the efficiency is good for the centrifugal fan. In terms of the application, they are used for dirty airstream condition where you have maybe the dust particle or fumes, right? So these are the generic application of the centrifugal fan. We can further classify, previously we classify the fan as into two categories, the axial fan and the centrifugal fan. Now the centrifugal fan, they have further classification. They are of radial centrifugal fan, forward curved centrifugal fan, and the backward curved centrifugal fan. Depending upon the direction of the blades, the curve of the blades relative to the direction of the rotation. As you can see, if the direction of the rotation is this one, this is the direction of the rotation, and the blade is facing backward, right? This is the direction of the rotation, whereas the blade is facing backward. So that's called the backward curved centrifugal fan, right? So if now if the this is the direction of the rotation, and this is the curved of the blades. Now the curved of the blades are in the forward direction relative to the direction of rotation. So those called the forward centrifugal fans, right? If the direction of the blades, right, is perpendicular to the axis of the rotation, now you can see this is perpendicular to the direction of the rotation, that's called the radial blades. Each one of this centrifugal fan has its own application, its own limitation, right? For example, the first one is the forward curve blade fan. This is one of the category of the centrifugal fan, as you can see in the figure, that the rotation and the direction of the curve of this is in the forward direction, so they are called forward curve blades. And this is the physical 3D diagram of the forward curve blade fan. These are used for, now this comparison is between the three category of the centrifugal fan, not with the axial fan. They are used for high volume and a low pressure application. Low pressure application mean up to 130 millimeter of the water column. So this is a gauge pressure, and they have efficiency between 60 to 65%, and relatively not, it's a medium efficiency, not very high efficiency, neither very low efficiency. So that means the medium efficiency when you say 60 to 65% efficiency, right? And the advantage is they are lighter in construction and they are less expensive, right? They are mainly used, they are suitable for the clean air environment, right? As the blade easily accumulate dirt. As you can see, if you look at that on the blades, these types of blade can accumulate the dirt here very easily. So that means the cleaning is, maintaining the fan is one headache. Cleaning is not so easy. If the a lot of dirt particle they are accumulated on the blade surface, that means that will increase another resistance, that will increase, that will be a part of the pressure loss again, right? That can decrease the efficiency of the blade. So that's why they are suitable for a clean air environment. Clean air environment, you can say maybe they can install, at the return, as a return air supply fan, not in the forward, because in case of forward there are more possibility that can have the dust particle if the filter they are not installed. So that's why it is recommended that before using this type of category of the centrifugal fan, a filter system should be integrated with that blower. Right? They are well suited for low pressure HVAC system, like the package air conditioning equipment. Normally the package air conditioning equipment that we have already discussed, they are normally installed for, let's say, a large building. So in those types of the HVAC system, the forward curve blade fan are recommended. So these are not constructed for high pressure or for the harsh service. Okay, the second category is the backward curved blade fan. As you can see, the blades, they are, curved in backward direction relative to the direction of the rotation. Compared to the forward curve, these are from low pressure to high pressure application, and their efficiency is much higher than the forward curve blade. I mean, as I showed you in previously, forward they have 60 to 65% efficiency, but relatively they are more efficient than the forward curve blade. But the disadvantage is they have the high maintenance cost, right? They produce more noise than the forward curve blades, right? And they are only recommended, this is very important, the backward curve blade fan, they are only recommended for clean air stream containing no condensable fumes or vapors, right? One of the common application is forced draft fan. I mean, the forced draft fan, they are very famous in the cooling tower, in the power plant. I mean, at the exit of the chimney, they are also installed as the forced draft fan. The third category of the centrifugal fan is a radial blade fan. Right, as I mentioned earlier, the direction is perpendicular to the axis of the rotation. So they are very straight. Neither the curve is neither in the forward direction, neither in the backward direction. That's very straight, perpendicular to the axis of the rotation. Right. I mean, radial compared to the previous two, their application is for high pressure, right? Compared to the forward and backward. I mean, they can produce pressure up to 1400 millimeter of the water column, right? But low flow rates, right? They have, I mean, more efficiency than the forward, but less efficiency than the backward flow direction. Their design is very simple. I mean, they're very easy to construct, right? Their applications, obviously, I mean, when you have heavily contaminated airstream like the dust laden, sawdust, etc., right? Whereas the previous two category, I mean, the forward curved or the backward curved, they are used for a very clean environment. So when your environment is not very clean, I mean, the dirty environment, then the radial fan, they are recommended and they are being utilized. Right, and they are also, I mean, generally they are for high pressure application when you need a very high pressure to create. Okay, second category of the fan is axial fan. As I mentioned previously, axial fan mean the direction is not changing. As you can see, we have a propeller and that propeller has a certain cross section, right? So that's why, because of the rotation of that, since the direction is not changing, in previous case, the high velocity was converted into pressure, whereas in that case, the air is pressurized by the blades, right? And which creating aerodynamic lift, right? Uh, Compared to this centrifugal fan, I mean, generally, I mean, when we compare centrifugal fan with the axial fan, centrifugal fan, they are for high pressure, whereas the axial fan, they are for high flow rate when you need to provide a large air volumes at a relatively low pressure than the axial fan are recommended. I mean, I'm comparing with the centrifugal fans. Centrifugal fan mean they are for high pressure, whereas axial fan mean they are for high volume flow rate, right? Their efficiency, they have a wide range of efficiency from a very low efficiency, 45% to 85%, right? Similarly, they have, I mean, from medium pressure up to 500, because more than 500 mean the high pressure. So that means they are typically used for the low pressure application, but a large flow rate of the volume, right? They have application with the industry where the size is an issue because they are very compact, their price is very low, and they are lightweight. They are very frequently used in the exhaust application, right? More or less every room they are, coupled with this type of the axial fan, in which they are frequently used for the fresh air intake or the as exhaust fan. The axial fan, again, they can be further categorized as propeller axial fan, tube axial fan, and vane axial fan. Propeller axial fan, this is one of the simplest axial fan. They contains two or more blades. You can see in that case, we have like the 5 blades, right? They are used for generating a very large volume flow rate, but a very small pressure, very low static pressure, as you can see. 20 to 50 millimeter of the water column. That's a very low pressure, but it can create a large amount of the flow, I mean airflow. right? They are low efficiency, approximately 50%, but they are very low price, right? They create, I mean, but the disadvantage, they create a large noise as well, right, relative to the pressure they have created. They are generally used for ventilation or as a exhaust fan. The second types of the axial fan is the tube axial fans. I mean, the fan is mounted inside a tube. I mean, this is just to increase the efficiency. When you mount an axial fan inside a tube, then the losses are reduced. This is to improve the airflow efficiency, right? They can create a static pressure from 250 to 400 millimeter of the water column. I mean, relative to the previous one, the simple, the axial fan, their efficiency is higher. I mean, up to 65%. They have the application in the exhaust, and in some applications such as drying ovens or paint spray, they are used as a tube axial fans. The third category is vane axial fans. As the name suggests, vanes, I mean, these types of their impeller or their rotor, they are mounted with the guide vanes. I mean, this is a rotating fan, but the air is guided through these fixed vanes. You can see these fixed vanes, right? So as a result, what happens by installing the guide vanes, the efficiency is improved. I mean, with the guide vanes, that improves the efficiency by directing the flow, right? They can have efficiency up to 85%. That means if the efficiency is more than 80, that means that's a very good efficiency, and that can be used to create pressure up to 500 millimeter of water column. So this is a maximum pressure that an axial fan can have. Again, they are typically used for high pressure application. Now, this comparison is between the three types of the axial fan. You cannot compare the pressure created by a centrifugal fan with the help of an axial fan. Axial fan mean they are for low pressure application, whereas centrifugal fan, they are for high application. This comparison is between the three categories of the axial fan. Now, let's discuss the important mathematical relations that are being used for the fans or the blower. One of the fundamental laws, which is also called the conservation laws, you are familiar with that. I mean, the flow through a pipe or a duct. I mean, steady state flow of any fluid. In case of duct, obviously the fluid is an air, right? The flow through through a pipe or duct is governed by the first law of thermodynamics, and you're familiar with this equation, P1 by rho 1, right? V1 square by 2gc, right? So these terms, the P1 is basically the static pressure, right? Rho is the density, right? V is the average velocity, right? I mean, when you put this bar, that means the average velocity, because in any of the duct or pipe, let's say this is a pipe, the efficiency is not constant. I mean, the efficiency which is near the surface of the pipe is lower. As you move in the center, the velocity is higher. I know you have studied the fundamental fluid mechanics and you know these concepts, right? So you can see the low velocity, then high velocity. So when we say that V1 square bar, so that means the average of that cross section. So, I mean, here you can have low efficiency that higher than maximum. So what is the average efficiency? So that is the average efficiency. So G is a constant, right? You're familiar that this is a gravitational constant, whereas GC is another constant, right? It has a constant value. I mean, for SI unit 9.81, or sometimes you can take 1. In case of the foot pound, 32.17, right? Z is an elevation, right? L is the loss head, right? W is the work. In case of fan, this is a work input, right? So, I mean, if you look at carefully this equation, each of the term in that equation has a unit of specific energy. I mean, each of the term in that equation has a unit of specific energy. And you know that what is the meaning of the specific energy? Specific energy mean, I mean, kilojoule per kg, right? So that's called, I mean, the energy per unit mass. So that's called, so each of the term, the first term that has a unit of specific energy, second also specific energy. So every term in that equation has a unit of the specific energy. I mean, one indicates, I mean, let's say, I mean, for any control volume. So let's say this is a duct, and duct can be very large, up to 5 feet or 6 feet. So let's say I'm talking about any of the control volume. So point one mean this one, point two mean this. So between any of the 2 points, right? So that's called the first law of conservation. I mean, the energy, sum of all of the energy at section one remains same at section two. So that's the conservation principle, that the energy remains same, right? I mean, at cross section two, some of the energy may be lost, or you can have the work input from the outside through the electric motor that drive the fan. So that's why these two terms are added at cross section 2, because at cross section 2, I mean, at outlet you have the work input from the motor as well as the friction effect, right? The conservation of mass, that means the mass at section 1 that remains same at section 2. So that's a fundamental equation. You're familiar with that. Again, that is an average velocity that you can also convert V1A1 in the form of flow rate. So density multiplied by flow is again the mass flow rate, right? The above equation, I mean, in the above equation, each term was, I mean, that has the unit of specific energy. You can also rearrange the above equation. I mean, you just multiply with the density, right? You multiply each of the term with the density, then each term in that equation has a unit of pressure. Now, this is a form of the conservation of energy. I mean, in terms of the unit is a specific energy, right? This form of the equation has, each term has a unit of pressure, right? The first term, I mean, P1 or P2, they are called static pressure, right? They are called static pressure. The second term, I mean, this term and this term, they are called the velocity pressure, right? The third one that called the elevation pressure, this is the elevation pressure, right? Whereas this one that called the pressure loss due to friction, right? So this, I mean, this is the same equation as the above equation, but the form is changed now. Now the each term has a unit of pressure, and each pressure, like this is the static pressure, the second one is the velocity pressure, the third one is the elevation pressure, and this pressure is the pressure loss due to friction, right? This is the pressure created by the motor, the work input, right? Similarly, we can have the third form of the fundamental equation. Now you just multiply, divide, and again divide with that term, Gc by G divided by rho 1. So if you divide with that, right, I mean, you multiply with that the above equation, then you will have another form of the above equation. This now each term has a unit of length, right? And this, they are commonly known as head. So that means the first term, that's called the static head, right? Static head. The second one called the velocity head, right? The third one called the elevation head. This is the elevation head. So similarly in the next equation. So each term now has a unit of length. So you can see the fundamental flow equation through a pipe or a duct, they can be represented in any of the form. They can be represented in terms of energy, specific energy, they can be represented in terms of pressure, or they can also be represented in terms of length. I mean, they are called, they are commonly known as head, right? And when we say total pressure in a duct or a pipe, that means the sum of the static pressure and the velocity pressure, right? In other word, when we use a word naught, P naught mean the sum of the static pressure and the velocity pressure, right? And similarly, in terms of head, I mean, the total head mean the sum of the static head and the velocity head, right? And lost head, I mean, that lost head IF, that's equal to F into L by D V square by 2G, where in that equation, F is a friction factor. That's called the Moody friction factor, right? L is the length of the pipe, D is the diameter of the pipe or the duct, and V is the average velocity in the cross section of the duct or the pipe. I mean, there is a difference if the pipe is a circular, so then we will use a diameter. You know that for a circular pipe, we normally use diameter. But a duct can be circular, it can be, I mean, the square, it can be rectangular cross section. So in that case, we use a different term. We call for a non-circular cross section, we use a term hydraulic diameter, DH. And the hydraulic diameter can be calculated by multiplying 4 into cross-sectional area divided by the wetted perimeter. So that's equal to the hydraulic diameter of non-circular cross-section. So by using this formula, we can calculate the loss head, right? Loss head. So that means these are related to the dimensions of the duct or pipe, the average velocity, and F. How to get the Moody friction factor F? Right? We can get that Moody friction factor from the Moody chart, Moody friction chart. But before that, we need the value of absolute roughness. There is a factor, it's called E, small e. That's called the absolute roughness, right? Each pipe has a different value of the absolute roughness. For example, you can see here the 5 different types of the material and the pipe. One, we have the commercial steel, right? Drawn tubing or plastic, cast iron, galvanized iron, concrete. So these are the common material that are used for the piping or the ducting material. You can see the least friction factor or the least roughness is from the plastic, right? Yeah, that's the least from the plastic, and the maximum is from the steel, the commercial steel. There is also a term, it's called the relative roughness. This is the absolute roughness E. When you divide this E with the diameter of the pipe or the hydraulic diameter of the duct, that term is called relative roughness, right? So the Moody chart is can be used to calculate that value of F, the Moody friction factor, and then you can have the loss head, right? So this is the chart. You can see the friction factor for a pipe flow, right? In that case, if you know the velocity, I mean velocity mean the Reynolds number, and if you know the relative roughness mean E divided by D, then you can read the value of the F. And there are different lines. For example, this is for the smooth pipe where you have the low value of the relative roughness, and as you move upward, you have the rough pipes, right? There is a range for the laminar zone, transition zone, and then the turbulence zone. So depending upon the value of the Reynolds number, you can have the different types of the flow. And from this graph, you can calculate the value of the F, the friction factor, and then you by putting this value of the friction factor in that equation, you can have the loss head. And then the decrease in total head, you can calculate from this formula, the difference of the total pressure divided by the density. And similarly, the total power imparted to the air can be calculated with the help of this equation. I mean, there's the difference of the total pressure. I mean, that's P01 mean at position 1, that's the total pressure, and M0 is the mass flow rate, and rho is the density of the fluid. And similarly, the static pressure can be calculated with the help of this formula, right? And the fan efficiency, that can be expressed in 2 ways. One is through the total fan efficiency. When we say the total fan efficiency, that's a ratio of the total air power to the shaft power. I mean, this is the power that is input from the electric motor, and the electric motor is coupled with the blower. So that's the input power, right? And this is the power that, I mean, the total air power, I mean, that is can be calculated with the help of either this formula or this formula, right? Sorry, this is the total power that is imparted to the air. So this one, right? And this is the shaft power. This is based on the electric motor that you have installed. From that, normally this is the rated input power. Normally this is mentioned on the nameplate of the electric motor. So we put both of the values. I mean, WT mean this value, right? And this that W shaft. So you can have the total fan efficiency. So what you need the flow rate of the air right? At inlet, what is the total pressure and what is the pressure at the outlet. So then you can have the total fan efficiency. So that will give you an indication of the fan efficiency, right? The fan, I mean, normally the units, they, I mean, in USA, the flow rate, they are normally taken in cubic feet per minute, and the total pressure, they are normally expressed in inch of the water gauge, and the power, I mean, the shaft power is normally represented in horsepower. So by putting these units, the above equation can be written, I mean, this factor can be included just for the unit conversion 6350. Similarly, the second way of expressing the fan efficiency is by using the static fan efficiency. Instead of total fan efficiency, you can also have the static fan efficiency. And the only difference is instead of using the total pressure, you can also use a static pressure. As you can see, instead here you are using uh, a total pressure, where in that equation, if you are using the static pressure, then that's called the static fan efficiency. This is the ratio of the static power input to the shaft power input. So again, for the unit conversion, you can use the same conversion 6350. So then the efficiency can also be expressed by using the units, United States units for the flow rate as well as the power in horsepower. Then we have the three fan laws that relate the speed of the fan, the power of the fan, and the static pressure. The pressure means the static pressure. I mean, the first law says that give you a relationship between the flow and the speed. If you're increasing the speed of the fan, then the flow of the air is increasing. I mean, the speed of the fan and the flow, they are directly proportional. So Q1 by Q2, I mean, let's say at this RPM, N1 mean the 1 RPM. So let's say initially the RPM was N1, the flow was, let's say, Q1. So if you change that, let's say N2, that will be Q2. So they are directly proportional. I mean, if you're varying the RPM by 10%, decrease or increase, so air delivery will be 10% increase or decrease, right? So that means they are directly proportional, flow and the speed. So this is the first fan law. The second fan law is the relationship between the pressure and the speed, right? So the pressure is directly proportional to the square of the speed. So now the pressure means the static pressure, right? So the static pressure has a relationship square of the speed. So sp1 divided by sp2 is equal to n1 by n2 raised to the square. So that means if you reduce the speed RPM by 10%, right? I mean, if you reduce that RPM by 10%, the static pressure will be decreased by 19%, and an increase in RPM of 10% will increase the static pressure of 21%. This is because the relationship is a square of the speed. Right? So that's the second fan law, that the relation between pressure and static pressure and the speed. Right? The third fan law is the relationship between power and the speed. Power is directly proportional to the cubic root of the speed. You can see this is the relationship between the power. So let's say this was kW1 at specific point 1, and it has a speed, let's say N1. So let's say if you, I mean, let's say this for any other of the point, that relationship is, I mean, if you increase the speed, the power will be increased. I mean, if you reduce the RPM by 10%, the power will be decreased by 27%. And if you increase the speed by 10%, the power will be increased by 33%. I mean, if you're increasing the speed, that means you need more input power to the fan. Let's say initially you need, let's say, 1000 RPM. So if you want to increase the RPM, then you have to increase the work input also. I mean, the power also. So that means, but I mean, let's say if you want to increase the RPM by 10%, you have to increase the power by 33%, right? So that means just for 10% increase in RPM, you need to increase the power 33%. So these are the fundamental laws for the fans. Then the next important question is how to evaluate the fan performance. That means the fan performance evaluation, right? So there are two way. One we call the with the help of the system curve, and then we have the characteristic curve, right? When we say the system curve, for example, this is one of the system curve that is I mean the relationship between the airflow rate and the total static pressure drop. I mean loss in static pressure, right? I mean if you are increasing the fan speed, that the pressure drop will be increasing. So that's called the system curve. I mean the system curve is the sum of the static pressure losses in the system, right? And they are also called the system resistance, which is a function of the configuration of the duct. I mean that decrease in pressure is a function of the configuration of the ducts, pickups, elbows, and the pressure drop across the equipment. Mainly this system curve that's used to determine what volume the fan will produce. I mean, if you know the static pressure loss, you can have the airflow. I mean, how much airflow will be will be produced by that particular fan, right? For example, you can see in that figure, for example, here, let's say this is a system curve for, let's say, any of the fan. You can see when the total pressure was 1.5 inch of water gauge, the RPM was 5,000. I mean, the airflow rate of the air that was delivered, that was 5,000 CFM. Let's say if that fan, the RPM is, let's say, increased, let's say that now the RPM is increased up to 1050 RPM, then what about how much is the power required? What is the flow rate delivered? So this is that will be calculated from the system curve, and that will be calculated from the three fundamental laws of the fan that I just discussed, that give you, for example, the first law that was between the speed and the airflow. Then we have the relationship between the speed and the static pressure. Then we have the speed and the power input required. So those three fans law that will be utilized to determine the or to extrapolate the value of the pressure, work input, or the flow rate for different RPM of the blower. And then the second way is a fan characteristic curve. I hope you are familiar with the characteristic curve. In fluid mechanics, maybe in the lab you have studied the characteristic curves of the pump. So similarly, we do have the characteristic curve for the fan as well. I mean, when we say the characteristic curve, that's a performance curve for the particular fan under a specific set of conditions, right? So and they are these characteristic curve, they are a graphical representation of a number of interrelated parameters, right? They are used to define the operating points. That's very important point. Basically the characteristic curve, they are used to define the operating points. I mean, what this, for example, any of the particular fan should operate at which point. I mean the point should be based on the efficiency, low noise, right? I mean, you will see what are the parameter for selection, right? So that means they will give you an indication that for that particular fan should be operated for which optimum operating condition, right? So there are three normally the characteristic curve. One of the characteristic curve is the relationship between the static pressure and airflow rate, the brake horsepower and the airflow rate, static efficiency, and the airflow rate. So normally these three characteristic curves are used in the fan to figure out the operating point as well as to figure out the optimum point of operation for that particular fan. Let me show you a few of the example. For example, these are the characteristic curves for the forward tip fan. As you can see on the horizontal, we have the airflow rate. So for different airflow rate, we have plotted the value of the, let's say, power, right? Similarly, we have plotted the value of the efficiency. Similarly, we have plotted the value of the pressure. As you can see, I mean, if you increase the volume flow rate of the forward tip fan, this is the one of the type of the centrifugal fan, you can see, I mean, the pressure is reducing, right? And there is a dip here. This dip is very dangerous. So you should not operate any of the fan near to that dip because there will be lot of noise. I mean, very close to that dip, and then it further increase and then it goes down. So as you can see, if the I mean, if you are getting a very large flow rate, right, but the pressure will be very low. I mean, on the other hand, if you are if your desire is, or if your application is a high pressure but low volume flow rate, then you should, I mean, this is your desire point. But obviously you should also focus on the efficiency as well. I mean, you can see the efficiency curve. If you're increasing the airflow rate, that means efficiency is increasing, but that increasing is for up to certain point. I mean, if you increase the further flow rate, then the efficiency of that fan will be increased. What about the input power? I mean, increasing the volume flow rate, the input power is constantly increasing. If you need a high RPM, that means you are increasing the speed. That means you are increasing the input power required. So you have to choose an optimum point for your specific application, right? What is the requirement for the airflow rate? So based on that airflow rate from the characteristic curve, you have to choose an optimum point or an operating point where you have the combination of high efficiency, low input power, and your desired pressure. I mean, at that particular condition space. So from these characteristics, you can choose your desired operating point. Similarly, we can have the characteristic curve. For example, here you can have the characteristic curve for the backward tip fan. Similarly, you can have the characteristic curve for the radial tip fan, and then you can also have this an axial fan. I mean, these three curves, they were for the centrifugal fan. I mean, this one for the forward tip, this is for the backward tip, this is for the radial fan, and this is the axial fan. So based on the characteristic of each of the fan, you can select your desired operating point. Each of the fan will have a different characteristic curve. So that generally that characteristic curve, they are drawn from the experiment. I mean, you change the volume flow rate and you measure different parameters and then you draw the characteristic curve. These characteristic curves, they are provided by the manufacturer, right? So that you can select your operating point, your desired operating point. So what is an operating point? The operating point is the intersection of the system curve and this static pressure curve, right? So when the system resistance changes, the operating point is also changing, right? Once the operating point is fixed, the power required could be found from the fan curve. Similarly, we can find the fan efficiency, just like the previous diagram. I mean, if you know one of the point, the remaining, I mean, the input power efficiency, you can very easily calculate that. For example, this is an example, let's say 12-1, in which let's say the centrifugal fan is operating as shown. So this is the operation of the centrifugal fan in which you have the flow rate of the air, let's say 5000 CFM, and the total pressure is 1.5 inch of Wg. The question is estimate the capacity, total pressure, and the power requirement when the speed is increased to 1050 rpm. So let's say the new speed is where is the new speed? Yeah, this is the new speed. So previously the speed was 900 rpm. So next speed is 1050 rpm. So at that speed, now what is the capacity now? What is Q2 now, right? And what is P2 now, right? Pressure and also the power requirement is also required, right? Initial power requirement was 2 horsepower. So initially the W1 was 2 horsepower. So which law we will use? We will use the fans law. So we have the 3 fans law. The first fan law is between the RPM and the flow rate. So we know the RPM and the flow rate and the second RPM as well. So from here we can have the flow rate. So you can calculate. Similarly, we'll use the second law. That law is between the static pressure and the RPM. So here we can calculate the P02. I mean this static pressure at RPM 1050. Similarly, the third power law is between the power as well. So you can have, if the RPM is 1050, then the power will increase from the power will increase from 2 horsepower to 3.2 horsepower, right? Okay, then this is very important. How to select a fan? I mean the fan selection. So what do you think? How can we have the fan selection? So let's say I have given you an assignment in the previous class. So let me ask how you will select your fan for that particular application. How can you select a fan? So Hamad Faisal is there.
Yes, sir.
So what do you think? How can you select a fan for that example that I have given you? So what input you need to select a fan?
Sir, the power required, the amount of heat dissipation that
No,
will be needed.
I mean you have to select the fan. I mean based on the previous slides that I have explained to you. First of all, you need the required capacity, right? Required capacity mean the flow rate of the air that is required, or flow rate of the air. How you know that? You have already decided from the heating and cooling load calculation. If you recall that how much is ventilation flow rate, how much is the air is required. So these calculation you have already done in cooling and heating load. So from there, I mean, the first input that would be required, that is the required capacity. कि कितनी capacity का fan required है. I mean, what flow rate is required for that air conditioning process, and that flow rate will be decided during the heating and cooling load calculation. Secondly, the second input that is required is the total pressure at design point. I mean zone, at the zone, what is the total design pressure, right? And that pressure will be considered by considering the pressure losses in ducts, joints and a diffuser. So basically you should have the total pressure loss. I mean, let's say if this is your blower, that is, I mean, fan that you have to select. Let's say this is your fan. So this fan has to deliver the air through the ducting, right? Ducting, joints, diffuser. So, and this is your, let's say, zone. This is your zone where you have to supply that air. So the first input that would be required is the capacity. I mean the flow rate, how much flow rate of the air is required, and that will be from the cooling and heating load calculation. The second is the total pressure at the zone. Total pressure at the zone mean, I mean, what is the total pressure loss? Because in the duct there will be a lot of, I mean, elbows, the friction effect, and the diffuser, the dampers. So the pressure drop, the pressure loss, that should be known to you. So if you know these two input, then you can select a fan, right? I mean, whenever you select a fan, you should have a good combination of the efficiency. I mean, for selection, you should, I mean, your first criteria should have a good efficiency, relatively low cost, low noise, and the compactness. I mean, physical size. I mean, your desire is that it should have low size as possible. The compactness is, the desire for everyone, right? So let me give you, I mean, from this is the ASHRAE chart from where you can select your fan. Let's say if you know that the desired capacity, I mean the flow rate, this flow rate is known from the heating and cooling load calculation. So let's say your desired flow rate is 8 CFM. Let's say this is your desired flow rate, and one more input is required. That's the pressure, total pressure loss. Right, so let's say the pressure loss is, let's say, 1.2. So then let's say you will have a point, where it cuts. So this is your, let's say, point. So at that point you can calculate your desired parameter. For example, you can see there is an efficiency curve. So this is an efficient, this one is a power curve. So you can have that how much is the power required at that position. Similarly, there is another curve, it's called the efficiency curve. So this is an efficiency curve. So you can calculate, you can see that what is the efficiency of here, because I mean, as I told you, for the fan selection, efficiency is the concern, right? and how much is the power input, similarly the noise, compactness. So from this chart you can see your optimum operating point based on the required capacity and the pressure. You can, I mean, the good zone can be plot. We have the graph in terms of logarithmic scale. So this is a logarithmic scale just to enlarge that area, as you can see. So you can read different values. For example, if you know this is your input, this is the input. If you know the capacity and the pressure loss, you can have different values. I mean, let's say for different RPM, you can read the efficiency, you can read the power input, right? So this is how you can select a fan. Similarly, this is for the forward curve blade fan. You can select even the tables, they are available based on different flow rate, right? And the pressure drop, you can select any of the fan, as you can see, I mean, based on the power input required, right? Then lastly, the fan outlet conditions. They are again, they are also very important. The fan outlet condition. As you can see, both the centrifugal fan and the axial fan. The first one is the centrifugal fan and the second one is the axial fan. As you can see, I mean, this is a cutoff point, right? This is a cutoff point. So because of that cutoff point, that area is called the blast area. So blast area is a slightly smaller than the outlet area. So this is the outlet area of the duct, right? So as you can see, as the air move into the duct, it is not fully developed, right? It is not uniform, right? So as you can see, it becomes uniform after a particular length, right? Even in case of the axial flow, as you can see, the flow is not uniform, right? The flow is not uniform. The flow becomes uniform after a particular length, right? So that length is called the effective duct length, right? The duct can be circular, it can be square, it can be rectangular. So any of the duct, it has a certain length after which the flow becomes uniform. So that called the effective duct length, right? So every blower should have a certain amount of the effective duct length. I mean, it should not be connected. Let's say if this is a fan, it should not be directly connected with an elbow. I mean, after having a certain particular length, which is called the effective length, then you should connect with some, let's say, elbow or something, any of the, fitting, right? I mean, this is to make best use of the energy developed by the fan, right? This length of the duct should be provided at the fan outlet. This is just to, I mean, to make the input of the fan as minimum as possible. This is both for the axial fan as well as for the centrifugal fan. And the preferably the outlet duct should be the same size as the fan outlet. So this is the fan outlet. So the outlet duct should have the same size as the fan outlet, right? This is an ideal. The effective duct length is a function of the fan outlet velocity. I mean, how to calculate? For example, what should be that effective length? What should be that effective length? That effective length is a function of the outlet velocity. So depending upon the velocity, I mean, how much is the outlet velocity of the fan? So that effective length is calculated. For example, this is a table 12-2 that give you an effective length for different outlet velocity of the fan. For example, at 2500 fpm, this is in British unit, this is an SI unit. So the different effective length they are being used. So depending upon the velocity, you can select the effective length, right? And in those cases, let's say in those cases where a shorter discharge duct length is used, so then what will happen? Let's say if the outlet is not outlet of the fan doesn't have an effective length, then what will happen? I mean, a short discharge duct length is used, then an additional pressure loss will occur, and this additional pressure must be added to the fan total pressure requirement. So this is an additional loss of the pressure. I mean, if you're not providing an effective length at the outlet of the fan, you are increasing the losses, you're increasing the pressure losses, right? So that's why the effective length of the fan should be accompanied with the outlet of the fan, right? And that how to calculate the additional total pressure losses, which is as a result of the shorter discharge. So that can be calculated with the help of this formula, C naught into PV, right? Whereas PV is a function of rho V divided by K, right? PV mean velocity pressure. This is the naught mean the total pressure, and C naught is a loss coefficient, right? That's based on the dis discharge duct area, right? K is a constant. It has a value in the SI unit as well as in British unit. British unit, it has a value of 1097, and SI unit has a 1.414. That's a constant. And sorry, K is a constant. Rho is a density. V is the average velocity, I mean, based on the cross section. So how to figure out that value of the C naught, which is called the loss coefficient. So if you know the C naught, you can calculate the loss in pressure because of the shorter discharge duct length. Right, so how to calculate C naught? C naught is calculated with the help of blast area ratio. As I showed you in the previous slide, the blast area is a slightly smaller than the outlet area of the fan. So the blast area is the ratio between the blast area. I mean, blast area ratio is the ratio between blast area to the outlet area, right? As you can see, different types of the fan, they have different blast area ratio. For example, backward curve, radial, forward curve, they have different value of the blast area ratio. Similarly, for the axial fan, they have different value of the blast area ratio. So if you know the blast area ratio, you can have the value of the C naught, right? As you can see in this figure, this is AB mean the blast area, A naught mean the outlet area. So this is basically the blast area ratio, right? The blast area ratio. So for different value of the blast area ratio, you can have different value of the loss coefficient. So once you have the loss coefficient, you can put this loss coefficient here. You can have the value of the total pressure loss, right? I mean, when the value of 1, I mean that the effective length is, I mean, perfect. I mean, the actual length is equal to the effective length. There is no loss. I mean, the loss coefficient is 0. So 0 multiplied by any of that, that means there is no loss of the pressure. Right? So depending upon the value of the blast area and the ratio between the actual length to the effective length required, then you can have the value of the loss coefficient. So after you have the loss coefficient, even the loss coefficient, I mean, depending upon the duct position, I mean the loss pressure loss because of the that duct, I mean the elbow, which is connected after the effective length, I mean the blast area ratio and the type A, B, C, and D. I mean these are type A, B, C, and D. You can have the value of the C naught, which is the loss coefficient. Right? So you can put that loss coefficient in that equation. Then you can have the loss, total pressure loss because of the elbow as well. Right? So that's the end of today's class. Next time we'll discuss duct design. I mean different types of the duct and the duct design. Right? Any questions?